Hi everyone, here we are on chapter 19.2, equilibrium. So equilibrium is based on what we call reversible reactions. So in a reversible reaction, we are going to have what is called a double-headed arrow in the reaction. So all of the reactions that we have learned so far only go in one direction, the forward reaction. So now with the double-headed arrow, it's going to show that it can go forwards and it can go backwards. Okay? And so what this means is that not all of the reactants are going to be converted into products, all right? So that says that right there. Not all reactions are going to be turned into products. You're actually going to have a mixture of both products and reactants in your container, okay? And this is also important to know. We know that we have reached this equilibrium point, so you should put a star next to this statement or highlight it. When the concentrations of all reactants and products remain constant with time. All right? So to demonstrate this, we're going to show in the next couple slides some examples of what that looks like. All right, so equilibrium, it can happen in many different ways. So in this example, this is club soda, which is basically carbonated water. In this picture right here, it's showing you, so notice that the lid is on, so it's a closed system. We call this a closed system. And obviously, if you remember, when you're looking at your bottles of whether it's water or soda or something, they never really fill the bottle up all the way to the rim with liquid. They always have like empty space, right, near the top here. So this is just the expanded form of what's happening between the liquid and that empty space. These are CO2 molecules. You can see here that we have some CO2 molecules in the liquid state, and then we have some here in the gas state, okay? And that's the empty space above the liquid part. All right, so what's happening here, you see these little arrows that are right there? That's showing you that these CO2 molecules are exchanging places at the same rate. Okay, so once again, in order for equilibrium to occur, these molecules are going to exchange places at the same rate simultaneously. So the forward rate equals the reverse rate. So therefore, we will always have the same number of molecules in the empty space and the same amount of molecules in the liquid state as long as the system is still closed, okay? But then notice what's going to happen. Once you open the container, then you're going to disrupt the equilibrium. You're not going to have the same amount of particles in the empty space versus the liquid. The equilibrium is disrupted because you had changed the system, you had opened it, so you can no longer have that reversible reaction. Okay, we also describe equilibrium as being highly dynamic. Highly dynamic means that the molecules and particles are constantly moving. Things are constantly in motion. Things in chemistry are typically described as being highly dynamic and not static. Okay, static means that the objects are not moving. All right. Also, remember that I had mentioned that in a reversible reaction, we use a double-headed arrow. So the double-headed arrow would look something like that. Okay, so what this is showing you, it's showing you that you have the forward reaction and then you also have the reverse reaction. Those two things are occurring simultaneously at the same rate. Okay? All right, so this is an example that demonstrates that we have reached the equilibrium point when the concentrations of products and reactant remain constant over time, okay? Remain constant over time. So let me explain this graph to you. Second here. Okay, so this should have a double-headed arrow there. All right, so that's the chemical reaction that this graph is demonstrating. So notice, nitrogen and the hydrogen gases are the reactants. So notice that those are the ones right here, right? Hydrogen and the nitrogen's right there. Notice what's happening to the reactants. Over time, the reactants are decreasing in concentration, okay, over time, and that's because, once again, they are being used up because they are reactants. The NH3, that is a product, notice that it starts at 0, but then over time it's being produced, okay, because it's a product. And then what you should notice here is that, see how these lines start to flatten out, or they start to remain constant over time? That's how we know we have reached the equilibrium point, okay? Once again, when the concentrations remain constant over time. This is just another picture that demonstrates the same idea, all right? So in this reaction, we're looking at how many like NO2 molecules versus N2O4 molecules, all right? They're probably on your notes, it probably shows the double-headed arrow there. All right, so initially when the reaction takes place, they're already counted here for you. We start off with 10 NO2 molecules. Once again, that's a reactant, so that's why we only have NO2. Then over time, the reactant is decreasing and then the product is increasing over time. More time passes, now we have 4 NO2s, okay? Now we have 4 reactants and now 3 products. Time again, progresses. Notice here, then we remain at 4 NO2 molecules, which are the reactants, and then we have 3 N2O4s, which is a product. So notice eventually 4 and 3, 4 and 3. Eventually, the concentrations stopped changing. They started to remain constant over time. So that is when we know that we have reached what is called our equilibrium point. All right, these are just some questions for a demonstration that I'm going to do in class. So I'll do this later during class time. So we'll come back to this. All right, now in order to have equilibrium, and some of these things I had already discussed, but we're going to review them. In order to have equilibrium, we have to have a closed system. Okay? In other words, it has to be in a closed container. The temperature must also remain the same, so you can't change the temperature. And just because we say that we are at equilibrium, it does not mean that we have a 50-50 mixture. Okay? It does not usually imply that we have equal amounts of products or reactants. All right, let's fill in the blanks here. Rate of forward reaction equals rate of, you can say reverse reaction, or you can say the backwards reaction. Okay, so the rate of the forward reaction equals the rate of the reverse reaction. Remember, those two rates are going to be equal. Now we're going to talk about the different equilibrium positions. All right, so we have a forward arrow and we have a reverse arrow, okay? Forwards and backwards. And notice that the arrows here are drawn in different sizes, okay? So in a chemical reaction, one side might be favored over the other. So notice that this arrow here, pointing towards the product side, is longer or larger than the other one. This is emphasizing that the products are favored. Okay, that the products are favored in that reaction. So that means that we have more products in our reaction than we do reactants. Then sometimes it might favor the other side, where you have a much larger arrow going in the reverse direction and then a small one going to the product side. So this is implying that the reaction favors the reactant side. So that means that we have more reactants in our mixture than we do products. And then this is an important piece of information. It says catalysts do not affect the equilibrium. So if we use a catalyst, remember they speed up chemical reactions, but they are not going to favor one side over the other. Okay, they're not going to favor the products and they are not going to favor the reactants. They will just help you reach that equilibrium point faster. Now, what if it was an inhibitor? Do you think the inhibitor would favor one side over the other? No, it won't. Okay, the inhibitor will just slow the reaction down and therefore it'll take longer to reach that equilibrium point. All right, now I'm going to show you how to write equilibrium expressions. So we use the capital K here, This is the equilibrium expression. So this is not Kelvin, okay? It's just a letter capital, it's just a capital K that represents the equilibrium constant. So when we write our expression for equilibrium, it's a ratio. Products are on top and reactants are on the bottom, okay? Notice here there is the use of brackets. Brackets represent concentration, okay? So the brackets represent concentration, which is molarity, or you can say moles per liter. So I'm going to show you how to write out these equilibrium expressions. There are more rules. Okay, so here we have an example. You guys have your arrows drawn on your paper. They get kind of messed up when they get downloaded into this program. Okay, here is our chemical reaction. So it's a ratio between products and reactants. So products go on top. Once again, the brackets represent molarity, or the concentration. And so look what happens to the coefficients here. Okay, so products on top, so C is a product, that goes on top, and look what we do with the coefficient. The coefficient becomes the power. Okay, so D, and then the coefficient becomes the power. So the products are on top, and then the reactants are on the bottom. Okay, and notice also here in these expressions, okay, look at this expression here. Notice that there is no plus sign between them. Okay, so those are being multiplied. All right. And then to solve a problem involving equilibrium expression, so you have to know how to write out the expression correctly, and then they'll give you numbers. You know, they'll say the concentration of C is this, and then D equals this, and you're going to solve for the missing variable. All right, so for this example, let's go to pen option. For this example, I want you to write out the equilibrium expression, okay? So we use a capital K for the equilibrium expression, and then we're going to do our products on top. Those go in brackets, right? So NO2, and then the coefficient becomes the power. So then this becomes to the fourth power. Okay, then we multiply that with the other product, which is H2O, and the coefficient is 6. Okay, then we go to the reactant side, and those go on the bottom. NH3, and that's to the fourth, and then O2, O2, and that's to the seventh power. Okay, so that's how we would write out the equilibrium expression. So then that's like our equation, and then all we have to do is plug in the numbers that the problem would provide. One thing I want to point out is that you do need to pay attention to the states of matter. Okay, only gases and things that are aqueous will go in the equilibrium expression. We do not put solids or liquids in the equilibrium expression because they are known not to really affect the equilibrium at all. Okay, so if you see a solid or a liquid, you kind of like ignore it as if it's not there. All right, so only put gases and things that are aqueous in your equilibrium expression. Now let me explain what this K value is telling you. The K value, once again, which is your equilibrium constant, it's going to tell you which side of the reaction that it's going to favor. Does it favor the product side, or does it favor the reactant side? Or is it at equilibrium? Okay, now here are some great things about K. It's a numerical value with no units, okay? So you're just looking at the number. It's a ratio that we take between products and reactants. And then notice here it says numerical value changes for different temperatures. All right, so you will have a different K value if you change the temperature. Once again, the K values are not affected by catalysts, therefore, which also means that inhibitors do not change the K value. Okay, so if your K value, put a star next to this one, if the K value is greater than 1, it favors the product side. Okay, you're going to have more products in your mixture than you do reactants. If the K value is less than 1, it favors the reactant side. So that means that you have more reactants in your mixture than you do products. Then something that you need to add to your notes, if the K is equal to 1, we say that it is at, that's an at sign, at equilibrium. Okay, and that's when the K is equal to 1. So those things you need to know. So when you're solving for K, you should always think back, okay, what is this number telling me? Okay, it's telling you whether or not the forward reaction or the reverse reaction is favorable. Okay, the last concept, all part of equilibrium, is what we call Le Châtelier's principle. So he's French, okay? So go ahead and read, let's read together, I guess, what his statement states. If a stress is applied to a system at equilibrium, the system changes in a direction to reduce that stress. Okay, so in other words, we are applying stress to a system. When we apply stress, that means we can change the temperature, we can change concentration, or even pressure. If we change any of those things, which is once again adding stress to the system, it's going to move away from the added stress. It wants to get rid of the stress. Okay, so then now we're going to talk about this more and go over some examples. All right, so the first thing we're going to talk about is how concentration will affect the equilibrium, okay? So it's going to shift away from the added component. So we say add away, okay? Now if we change the temperature, okay, so now if we change the temperature, you have to see where the heat is being added to in the chemical reaction. So let's take a look over here. There should be, the double-headed arrow should be over here. Once again, it got moved over there and it really shouldn't be over there. Okay, so it should be written correctly on your notes. All right, so in one situation, you have the energy on the reactant side, and then over here, we have the heat on the product side. So for the temperature, you have to pay attention where the heat is being located. Okay, so it will move away from, once again, the added component. So if we add more energy, okay, it's going to move away from itself. It would shift to the right. Or if we look over here, add more heat, increase temperature, it's going to move away from the added component. Okay, so that will tell us which side it will favor. So let's take a look here at this example. As you can see, this is the chemical reaction that's happening. We have N2 plus H2, and it makes us NH3. All right, so what I want to do is I want us to count up how many ammonia molecules we start out with, and then how many we end up with when we change the concentration of nitrogen. Okay, so NH3, the molecule is this one right here. So we start off with 1, 2. Okay, so we start off with 2 NH3s. Now notice what happens. Now we're going to add more nitrogen. Okay, notice where nitrogen is on this in this chemical reaction. It's right here. Okay, so you're adding more nitrogen. Remember, if you are adding more concentration, it wants to move away from the added component. So add away. Okay, so it's on this side of the arrow. So we say add away. They both begin with the letter A. So that means that by adding more nitrogen, it's going to cause the equilibrium to shift to the right, okay, because it wants to move away from the added component. It wants to get rid of it. So once again, add away. So it's shifting to the right. So we can predict that we're going to make more NH3 in solution. So then let's go ahead and add up the NH3 molecules. There's 1 there, 2, 3, 4. So we end up with 4 NH3 molecules. Okay, so then you can see that our prediction was correct. With the add away concept, it was telling us that the reaction would shift to the right, making more product. And that's exactly what we see here. We start off with 2 NH3s, you added more nitrogen, and we ended up with 4 NH3s. The last type of stress that we can add to a system, we're going to talk about pressure. Okay, and when you think about pressure, think about a container. So if we start off with a container, let's say this big, okay, and then I'm going to make the container, let's make it much larger, okay? So now I made the container larger, right? So look at the space here. If the container is larger, that means we have less pressure because now there's more room for the particles to move around in. So that means it's going to favor the side that has more moles. Okay, it's going to favor the side that has more moles. So you're probably wondering, well, how do I figure out which side has more moles? What you do is you add up the coefficients on both sides of the arrow. Okay, so you add up the coefficients on the reactant side and you add up the coefficients on the product side. And then the side that has more moles, because this is a larger container, then that side is going to be favored. It will shift towards that side. Now, what if we have the opposite? What if we start off with a very large container and then I make the container much smaller? Okay, look at the space here. This is a very small space. So this is going to favor the side that has fewer moles. Okay, favors the side that has fewer moles. Once again, add up the coefficients on both sides of the arrow. Whatever side has the least amount, then that's where your equilibrium is going to shift towards that side. Now, sometimes you might have equal mole amounts on both sides of the arrow. If that is the case, then there will be no shift in your equilibrium at all. Okay, so once again, if you have equal moles on both sides, no shift. Okay, so here's a picture to demonstrate that. Notice we're dealing with the same chemical reaction. And what I want you to do is we're going to add up the NH3 molecules that we start out with and the amount that we end up with. All right, so let's see. So here we start off with 1, 2. Okay, so we have 2 NH3 molecules. Now look what happens to the pressure. Okay, they're decreasing the volume, therefore the pressure is going up. Okay, so we changed the pressure by changing the volume. Now we have to figure out which side is this equilibrium going to shift towards. Okay, so you have to add up the coefficients on the left and add up the coefficients on the right. So over here, it's a coefficient of 1 plus 3, so that's a coefficient of 4. Okay, so this side has 4, and then this side only has 2. Now we take a look at our picture, compare, this is what we started out with, now they're making it smaller. Okay, so now that it's smaller in size, this is telling me that it's going to favor the side that has fewer moles. Okay, favors the side that has fewer moles. So 4 here versus 2 there. So once again, it's a smaller space. It's going to favor the side that has the least amount of moles. So therefore, it's going to shift to the right. So we are going to assume that this is shifting to the right. Now let's double check by looking at the picture to see if we are right. So then we ended up with 1, 2, 3, 4, 5, 6. So then we end up with 6 of the NH3 molecules. Okay, so look what happened. We started off with only 2 of them, then we ended up with 6 of them. So that is telling me that our prediction was correct. We are indeed going to shift towards the right-hand side, right? As it's shifting to the right, you're making more product. It's pointing towards the NH3, okay, the side that has fewer moles. All right, so now what I'm going to do is I'm going to do some sample problems from the equilibrium worksheet. You will find this worksheet in your folder. So the first example that I'm going to go over, we'll just do the letter A one, that's right here. So for number 1, all they want you to do is write out the equilibrium expression. So when you write out your equilibrium expression, that's products over reactants. Okay, and we use brackets to represent concentration. So N2O4, okay, bracket, and that is just to the first power. All right, so this is the one we're doing. So products on top, and then the reactant here is going on the bottom. So then NO2 in brackets. All right, so NO2 in brackets, and it has a coefficient of a 2, so then that number will be squared. So that's all you have to do for number 1, is do the expression, products over reactants, coefficient becomes a power. Now I want you to make sure that you're careful on some of these. So I want you to be careful or pay attention that this is a solid, okay? And then some of these other equations have solids in them. Remember, solids and liquids do not get included into the equilibrium expression because they were found not to affect equilibrium at all. So you just kind of, when you're writing out your expression that has a solid or a liquid, you just pretend it was not there, okay? You kind of ignore it like it's not there. All right, so let's do one of these math problems together. Let's just then go ahead and do number 2 here, okay? So you can see that this is the chemical reaction. It gives us the concentrations of S2, O2, and SO3. And then it says at the temperature of the equilibrium mixture, calculate the equilibrium constant Keq. Okay, so I do want to explain what this EQ means. Sometimes, remember, it's a capital K that is being used to represent the equilibrium constant, but sometimes people get confused between this K or the K for Kelvin. So to distinguish between them, sometimes you will see a little subscript EQ underneath the K like that to represent that they're talking about equilibrium and not temperature. Okay, so let's go ahead and solve for this Keq. I'll just help you set up the problem. All right, so Keq, so products over reactants, coefficient becomes the power. So SO3, okay, and that's to the second power, over, so 2 SO3, okay, over the reactants, which is SO2, and that's going to be to the second power times O2, and that one only has a coefficient of 1. So this is our equation. Now we're going to plug in the numbers. Okay, so SO3, so let's look at the numbers. So SO3, we are going to plug in 0.15. Okay, 0.15, and then that is going to be squared over, so SO2 corresponds to 0.75, and then that number is squared, and then O2 is also going to be on the bottom, and the O2 is 0.3. All right, so then you put that into your calculator and then see what you get. All right, so let's go ahead and do that. Okay, so if you do this correctly, I got 0.133. Okay, and that is my K value. So once again, I want you to always think about, like, what is this number telling me? So remember, the K value is telling you which side it's favoring. Does it favor the product side, the reactant side, or it could be at equilibrium? Well, look at this number. The number is 0.133. So that's telling me that it is favoring the reactant side. Okay, so if the K value is less than 1, it favors the reactant side. So it's telling me that in the mixture for this reaction at those concentrations and temperature, that the reaction mixture contains more reactants than it does products. Okay? And that's about it. So go ahead and continue working on this worksheet. You should be able to get this done by the end of the period. Okay? All right, I will see you later. Bye.